All right, Math 2, here we go. We've got our first lesson in Unit 10, quadratic graphs. Our question today are, what are the similarities and differences between the characteristics of these two functions, f of x, which is 3x squared plus 2, and then g of x, which is 1/3 x squared minus 2. So using f of x and g of x, these are, remember, your y values. This is just a way for us to refer to them. So if you say f of x, I know you're talking about this one. If you say g of x instead, I know you're talking about that one. So this is just a way to name these functions so that we can easily talk about them and we don't have to write the entire function. Anyway, when I say characteristics, I want you to talk about their widths, whether they have minimums or maximums, where their vertex is at, and their domain and range. And that's what we're going to talk about throughout this. We're going to be talking about what kind of characteristics do our quadratic graphs have, and how can we look at the equations and notice these characteristics. So here we go. First of all, what we need to know is that our quadratic graphs are going to make a parabola. So this is a parabola right here. How do we get a parabola? It's from having an x squared in our function. So basically, we need a function to the second degree. So if you've got a polynomial to the second degree, so there's like an x squared is your highest, variable to the x power or whatever. If it's to the second power, it's going to make this parabola. A U-shaped graph, it's going to be made of curves. And this graph is special in a few ways. Number one, it's special because when we did linear equations, they either always increased or always decreased. On this one, it's decreasing over here. So on this side of the graph, it decreases. And on this side of the graph, it's increasing. So the first thing we notice about these parabolas is that they increase and they decrease. It's because at this little point here called the vertex, they change directions. Now, another interesting thing about parabolas is that they can be split in half. And when you split these in half, they create mirror images of each other. So on either side of this dotted line, the two sides would look exactly the same. They'd just be a reflection of each other. And this line we call the axis of symmetry. So that axis of symmetry line is like a line that magically goes through the middle of our parabola and cuts it into two reflected parts. So parabolas are always going to be a mirror image on either side of the vertex. So mirror image, we could also say a reflection. All right, so when we have the standard form for quadratics, it's going to be in the form of f of x, or you remember f of x is y, so you can say y equals ax squared plus bx plus c. What this means for the a, b, and c, these could be numbers. So this could be like 3x squared plus 2x plus 5 or something like that. This would be standard form. Notice it's in descending order. And again, like we said before, our biggest exponent, or our highest degree, is to the second power. So anytime we have a second power as our highest degree, it's going to make a parabola like this. It's going to make these U shapes. Okay, so the vertex, we said this was the vertex on this one. The vertex is the coordinates of the highest or lowest point. This particular one has a lowest point. And so that's the vertex. The vertex is basically where the parabola changes directions. So we see that it was decreasing over here, and then it changed directions and increased over there. The point where it changes those directions is the vertex. When we have a minimum, the vertex is the lowest point. So right there, we have the lowest point. That's what we would call a minimum. So a minimum is when the vertex is down here. That's a minimum. Now, our parabolas do not have to always face up like a smiley face. We can have a maximum where the vertex is the highest point instead. So if our parabola faces down, like a frown face, then our vertex would be a maximum instead. So minimum and maximum are both the vertex, except the minimum is when the vertex is the lowest point, and a maximum is when the vertex is the highest point. Next is the parabola width. Okay, so it's how wide the parabola is. So you can have parabolas that, are really wide like this, or you can have parabolas that are really skinny or narrow like this. So the width of the parabola can change based on the equation. And the number that tells us how wide or how skinny it is or how thin or whatever is the a value. So the number in front of x squared tells us this. And I put absolute values around this because we're going to ignore if it's a positive a or a negative a. So just look at the a value. So if you have a bigger a value, then that makes your parabola skinnier. So the bigger your a value, like if you've got a parabola looking like this, and you've got a big a value, it's going to make it skinny like this. If you've got a small a value, it's going to be a really wide parabola like that. So the smaller the number, the wider it gets, the bigger the number, the closer together it gets, and the skinnier it gets. So this would be a big or a small a value. And this would be a big a value. Now what's big and what's small? Well, it depends. This really doesn't come into play unless we're comparing two different parabolas. So we talk about their width when we compare one parabola with another one. So the one that has the smaller a value is going to be wider, and the one with the bigger a value is going to be skinnier or narrower. The domain, you've done that before in Math 1. These are your possible x values, and your range is going to be your possible y values. All right, so these are the characteristics we want to look at when we compare two different parabolas. Let's do our first one. Now this one is in the form of ax squared. Notice there's no bx and there's no c. So we're missing the bx and we're missing the c. So we're just looking at, and in this case, a is equal to 2. So bigger a values mean it's going to be more narrow than most parabolas would be. So if you had another one where the a value is 1, this one would be narrower than it. Okay, let's go ahead and do a table of values so that we can graph this. Okay, table of values. Let's go ahead for our x and for our f of x. Usually what I would pick for this type of problem would be -2, -1, 0, 1, and 2. I would pick 5. Now one of these 5 is our vertex, and we're going to get to that in a second. So let's just plug in -2 into the function. So if I did 2 times -2 squared, well, -2 times -2, because we have to square first, would be 4. And then 2 times 4 is 8. So when I plug in -2, I get 8. Let's plug in -1. If I plug in -1 into the function up here for x, -1 times -1, because I'm doing the squaring first, would equal +1, because a negative times negative is positive. And then 2 times 1 is 2. So my f of x value when x is -1 is 2. Let's plug in 0. 0 squared is 0. and 2 times 0 is still 0. Let's plug in 1. 1 squared is 1, and 2 times 1 is 2. Over here, we'll plug in 2. 2 squared is 4, and 2 times 4 is 8. Now notice what happened here. On either side of this 0, this number and this number are the same. And then this number and this one are the same. And it makes sense because they're mirror images. On either side of that axis of symmetry, they'll be exactly the same because they're mirror images. So we want to see that. We want to see the same number on either side because it's a mirror image. Okay, so 0, 0 is going to be our vertex. I'm going to plug in 1, 2. So 1, 2 would be about right here. And then 2, 8. 1, 2, 3, 4, 5, 6, 8. That goes up to 8. Would be about right here. Now if I plug in -1, I get 2. So -1, 2. See where we're getting there? We're getting that mirror image. It's the same on either side. And then if I plug in -2, I also get 8 up here. Okay, so there's our parabola. I'm going to use a pencil so I don't mess this up. So this is a U shape. You may be asking yourself, well, why is it so narrow? Why is this one not spread out like you usually see U shapes? And the reason is because of that A value right there. That A value was 2. So when you have an A value of 2, it causes your parabola to be narrow. So there's not a lot of width right here. Okay, our vertex is down here, and that vertex is a minimum because it's the lowest point. So our vertex is at 0, 0. Now, anytime you don't have a BX and you don't have a C, your vertex is going to be at 0, 0. So this one didn't have a BX, it didn't have a C, so it's going to show up as a vertex at 0, 0. And then we can see that our axis of symmetry is right here along the y-axis. That's where it's splitting it in half, and it's the same on either side of that. Let's talk about its domain. Our domain for this one, remember, is all of the possible x values. Well, we plugged in 0, and that was a possible x value. We plugged in 1, that was a possible x value. We plugged in 2. I can keep on plugging in numbers here forever, and I'll get values for y. So we would say that the domain is going to be all real numbers. There's a couple ways we know that. Number one, we know it because I can keep on plugging in new numbers here, and I'll get an answer. There's no x value that I would plug in where I wouldn't get an answer for y. The other thing that I see is, you see, even though it's pretty narrow, this thing's getting wider and wider. That means side to side, because your domain is always the x values which go side to side. Side to side, this thing's going to keep on opening up more and more and more, which means, and since we have infinity to play with, this is going to keep on going, getting wider and wider forever, which means nothing's stopping this graph from going left and nothing's stopping this graph from going right. It can go left and right forever and ever, which means your domain can be any number you can think of, all real numbers. The range, however, is found by looking at your y values, and your y values go up and down. Now on your y values, you do have a lowest point. This graph will never get down here, right? Because it gets down to 0 on the y, because our vertex is at 0, 0. So the y value is 0 down there, and then it turns around and goes the other direction. So down here, our graph never makes it down to this part. So that means that our range can only be 0 or bigger. our y values are always going to be 0 or bigger than that because our graph is never going to make it down to this negative territory for y's. So what we would say is the y values have to be equal to 0 or greater than 0. So they can be equal to 0 right here, and then all these points are greater than 0 for the y values. Again, we're only looking at the y values, and these are all our y values. None of them are negative. So it's either equal to 0 or greater than 0 for our range. All right, example 2. And that's the bump. All right, so example 2, here's another one. Notice that this one is also missing the bx and the c. So we've got ax squared plus bx plus c. And in this particular problem, all we have is the x squared. The bx is missing and the c is missing. Now remember, that tells us that our vertex is going to be at 0, 0 for this problem. Now our a value here, our a value is -1 because the number out front here is a -1. All right, we're going to compare example 1 and example 2 in a little bit so we can talk about width. But let's go ahead and graph this one first. So I'm going to, again, choose for my x's. I'm going to use -2, -1, 0, 1, and 2 again. I want to choose 5 numbers because I want 2 on one side and 2 on the other side so I get a really good idea of how wide it is or the shape of our parabola. So I'm going to plug this in. So instead of x, I'm going to plug in -2. So the negative stays out front, and then -2 squared. So this would be negative, and then -2 squared is 4. So we get -4. For this one, we plug in -1, square it. -1 squared is +1. And then we have a -1 outside, so -1 times 1 is -1. When we plug in 0 and square it, 0 squared is 0, and -0 or -1 times 0 is still 0. Let's plug in 1. So when I plug in 1, 1 squared is 1, and then I have a negative out front, so this becomes -1. See, we're getting that same number there. It's because it's a mirror image. It's a reflection across the axis of symmetry. And you might have predicted it already. We should get -4 when we plug in 2. And we do. We get -4. All right, graphing this. Our vertex is at 0, 0 again. Remember, it's 0, 0 because there's no bx and there's no c. We're going to get our vertex at 0, 0 every time when that happens. It's just like the last problem. Okay, let's graph these other points. 1, -1 would be 1, -1 right here. And then 2, -4. So 2 and then -4. 1, 2, 3, 4. Yep, it's right about here. Okay, then on the other side, -1, -1. And 2, 4, -4. I'm going to use my pencil. If I can find it. It's stuck on my sleeve. Sweet. All right, so we get this shape this time. All right, let's compare these two. It's hard to compare them this direction. Let's just compare them facing the same direction. Now we can see this one is slightly tighter than that last one. So see, it's more narrow than this one is. And it's more narrow because the A value for our first one was 2. So that made a narrower graph. And then over here, the A value was 1. Remember, we don't worry about the negatives. So the A value is 1. And so on this one, it's a little bit wider. So the bigger the A value, the wider the smaller the a value, the wider the graph. So this is a smaller a value, it's 1, and that made this graph wider. If I would have made it even smaller by did like a value of 1/2 or something like that, then it'd be even wider than this one was. Now the other thing that's different about this one is that this one has a maximum at the vertex. Now what was different from this one compared to our last one? Well, this one had a negative a value. And anytime our a value is negative, that's going to make our parabola face down and have a maximum. So if a is negative, the vertex is a maximum. Again, look at the previous problem. On our previous problem, the vertex was, or the a value was a positive. Positive a values face up. Negative a values face down. So here we had a minimum, and we had a minimum if a is positive. The vertex is a minimum. So positive a value, we get it facing up because our a was 2. Negative a value on this one, it gets us facing down, so we had a maximum instead. Let's look at our domains and our ranges. Our domain, remember this is going left and right. This is going to keep on getting wider and wider and wider, which means left and right, there's nothing from stopping it from going any direction. So it's going to keep on going this way, and it's going to keep on going that way. So we're going to say our domain is all real numbers. Our range on this one, this time our range is all the negative values down here. And our range is never going to get up here in the positive area. So our range, our y values, can be equal to 0, but then not greater than 0. All of our y values are negative numbers. So they're all going to be less than or equal to 0. Because from this point down is where our graph shows up. Okay, so for these sets of notes, we're not going to worry about bx. We're going to get to that in a different set of notes. But if I added a c value, okay, I haven't had a c value yet, but if I add a c value, it's going to shift our graph. So if I have a c value, it's going to shift the parabola up and down. What does that mean? It means if I added a positive 1 right here to this equation, this whole graph would move up one space. The vertex would be here, this point would be here, this point would be here, and this point would be here, and this point would be here. Everything would move up one space. If my c value for this last one was like, if it said negative x squared plus 3, this one, or minus 3, sorry, minus 3, it would have shifted it down. This one, vertex, would have ended up down here because it would have shifted down 3 units. This one would have shifted down 3 units, down 3 units, down 3 units. Everything would have moved down 3 units. So that's what the c value does, is it shifts our graphs up if it's a positive number, or it shifts our graphs down if it's a negative number. So let's look at what we've got here. We've got two functions. F of x is just where we have ax squared. Now the a value is 1. There's no bx, there's no c. On this one, h of x, this is our ax squared, so our a value is 1. So since they have the same A value, they should have the same width, right? But our C value, this is our C value. Our C value is 2. So what does this mean? It means that these graphs are exactly the same, except h of x is shifted up 2 units. Okay, let's prove that. So I'm going to do a table of x and f of x. I'm going to do -2, -1, 0, 1, and 2. Okay, so if I square -2, I would get 4. If I put -1 in here, I'd get +1. If I put in, instead, if I put in 0, I'd get 0. If I put in 1, I get 1. 2, I get 4, because I'm squaring all these numbers. Okay, graphing that, 0, 0. Remember what I said, anytime the A value, where there's just an AX squared and there's nothing else, we get 0, 0 as our vertex. So there's our vertex. And then we're going to get 1, 1. So this point here and this point here is -1, 1. And then 2, 4 and -2, 4. So 2, 4, we're going to say is about there. And -2, 4 is about here-ish. All right, so there is our parabola. All right, so this is a shift up of 2. So what should I expect? I should expect that these two equations, or these two functions here, they should be the same, except h of x is going to be moved up 2 units. So everything should move up 2 units. Let's see if that actually happens. So I'll do x and h of x. So -2, -1, 0, 1, and 2. All right, so let's plug in -2 into here. So if I -2 squared, and then I'm going to do +2. So this is 4 plus 2, which is 6. For this one, I plug in -1, and I get 1 plus 2, which is 3. If I plug in 0, 0 squared plus 2, so that's 0 plus 2, and I'd get 2. For this one, I plug in 1, and it's going to be the same as this one, because remember, these are mirror images. So I do 1 squared plus 2, which is 1 plus 2, which is 3. Then I plug in 2. 2 squared is 4, plus 2 is 6. Okay, so graphing this one, our vertex is now at 0, 2. 0, 1, 2. See, this one moved up 2 units. This point's at 1, 3. 1, 1, 2, 3. So this point moved up 2 units. And this point's at -1, 3. So that also moved up 2 units. And then 2, 6 would be right here. And that point moved up 2 units. And then -2, 6, this point over here also moves up 2 units. So what we have here is the exact same parabola. It's just the C value has moved it up 2 units. So adding a C value shifts the graph up 2 units. Why is the second one a better looking parabola? I don't know. Oh well, moving on. So the C values shifted. If this would have been a -2, this would have moved down 2 units instead. All right, so example 4. Which graph is the widest? Well, before we get to that, let's say what these values are. This is an A value of -4. This is an A value of 1/2. This is an A value of 1 because the number in front is 1. This one does not have a C value. This one has a C value of 5. and this has a C value of -3. All right, which is the widest? Well, the widest one is going to have the smallest A value. So g of x has the smallest A value. So we would expect that that graph would be the widest graph. So 1/2, or g of x, because it has 1/2. Okay, this one should be the most narrow, because 4 is the biggest number. Remember, we don't worry about the negatives for width. So g of x is the widest graph. Which graph has a minimum? Well, when the A value is positive, it faces up. So that one would face up. This one has a positive A value, so it would face up. This one has a negative value. That would make it face down. So which graph has a minimum? G of x has a minimum, that has a lowest point, and h of x would also have a minimum. So g of x would have a minimum, and h of x. Which has a vertex at 0, 0? That would only be f of x. Why? Because this one got shifted up 5 units. So this would have a 0, 0, but then this would move it up 5 units. So this vertex would be at 0, 5. This one has a C value of -3, so that would move it down 3 units. So that one's vertex would be at -3. So this one would have a vertex of 0, 0 because it doesn't have a C value. Which has the lowest range value? Which one has the lowest possible Y value? Well, it has to be this one. Why, Mr. Holcomb? Well, because it's going to infinitely go down, 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 down. So this can get infinitely low on the Y values. And the range is our Y values. So this one has the potential for getting the smallest Y value possible because it's facing down. So that's going to give us our smallest Y value. Now, if I were just looking between these two, then I would have to say, oh, it's going to be this one. Because this one's vertex is at 0, -3, but this vertex is at 0, +5. So this is our Y value for our vertex. So that one would be lower. That is all I have for you today, my people. We're going to really get into these quadratics. In fact, we're going to do so much with these quadratics, we're going to take 2 units to do it. So this is just the very tip of the iceberg where we're looking at our characteristics of our different quadratic graphs. All right, I will see you next time. Math hard. Bye-bye.